slides. Here we go. Hello, everyone. I'm Maura Pintor, and I'm a co-organizer of this live series event in about machine learning security. Today we have as a guest Yizheng Chen from University of Berkeley. I want to share a few information, like a little information before we start. First thing, the event is live streamed and recorded. So if you don't want to be recorded, you can follow from the YouTube link. For the questions, Yizheng kindly let us know that you can ask questions also during the talk. Otherwise, at the end of the talk, we will give some space to you. So if you're in the Zoom call, you can raise your hand and you will have top priority in the questions. Otherwise, you can type in the Zoom chat, or eventually, if there is time left, we also check questions from the YouTube chat. Follow us on Twitter, LinkedIn, Eventbrite, or in all the links that Luca will kindly share in the Zoom chat and in the YouTube chat now to receive updates on the future events. And if you are new to the field of machine learning security and you want to know more, we also have a course in the same YouTube channel where we are live streaming right now. And lastly, let me thank all people who helped me organize these events. And now I leave the stage to Ambra, my colleague, who will introduce our speaker.
Good morning to everybody. Today, we will have Yizheng Chen as an invited speaker. Yizheng is a postdoctoral scholar at the University of California, Berkeley, and she will join the University of Maryland as an assistant professor of.
Sorry, Ambra, I disabled your audio. Please, all speakers, all people joining, please mute yourself, otherwise we have problems. Sorry, Ambra. Go.
No problem, Don. I was saying that Yizheng is a postdoctoral scholar at the University of California, Berkeley, and she will join the University of Maryland as an assistant professor of computer science in January 2023. Previously, she was a postdoctoral scholar at Columbia University. She held a PhD in computer science from Georgia Institute of Technology, and her research focuses on building robust machine learning algorithms for security applications. Her work has received an ASIAM CCS Best Paper Award runner-up, a Google Aspire Award, and an Amazon Research Award. Moreover, she is a recipient of the Anita Borg Memorial Scholarship. So I'm really happy to leave the stage to Yizheng that will deliver his talk, which is entitled Learning Security Classifiers with Verified Global Robustness Properties. So Yizheng, the stage is yours.
Thank you for the kind introduction, and thank you for inviting me to be here. Let me share the screen. Okay, I hope it's working.
Yes, it is.
Okay, that's great. I'll get started. So my talk's title is Learning Security Classifiers with Verified Global Robustness Properties. This is the paper published at CCS last year and won the Best Paper Award runner-up. This is joint work with my co-authors Shiqi, Yue, Xiaojing, Suman, and David. So nowadays, we can use machine learning to solve many security problems, such as detecting malware, advanced persistent threats, online fraud, and many different kinds of malicious activities. We can build very effective detection algorithms, but these techniques are built on a fragile foundation. It is easy for attackers to evade machine learning-based solutions. Now to demonstrate what I mean by evasion, I'm going to use the Twitter spam account classifier as the running example throughout the rest of the talk. So many previous works have demonstrated that we can use features such as the length of a Twitter account username, the length of profile description, number of tweets, number of following and follower accounts to detect whether an account is a fake account or a real account. Spammers will set up fake accounts to spread harmful information like links to download malware or phishing content on Twitter. So these features work really well because usually benign users behave differently from malicious users. For example, malicious users will try to follow a lot of other people in hope of getting some followers back. So they will have different feature values. So if we use those features, we can very accurately detect what are the fake or malicious Twitter users and what are the benign ones. Now, for an attacker who actually controls these fake Twitter accounts, they can change something like this. Like they can change the number of followers, delete one followers by blacklisting an existing follower. And such small change is possible to evade an existing Twitter account classifier and make the account classifier predict a malicious user as benign one. What existing defenses can do to prevent this type of evasion is, so existing defense can verify that given an input, here it's a Twitter account and its corresponding features, similar inputs would have the same malicious prediction by the classifier. For example, similarity is defined by if you just change the number of followers slightly from 10 followers to between 8 to 12 followers. Now you have a small range of change. And any change within this range, which form a new input, the classifier can still predict the new input as malicious. So existing defenses can even integrate this verification and train classifiers to make most inputs robust. So these are training techniques that include adversarial training, certifiably robust training, and randomized smoothing techniques. What the guarantee tells you is they can ensure something called local robustness, that after training and after deploying these techniques, the robust classifier will be robust for some inputs, but not all inputs. So the problem with such local robustness guarantee is for some inputs, there is no robustness guarantee. For example, when we have a new evil user 2 with a new profile description, even with the same number of following and follower accounts, now the attacker can do the same type of attack, like modifying the number of followers, decrease the count by 1. And because it's a new input, now you can evade the class. It could successfully evade the classifier again and make it predict the evil user 2 as a benign user. So in this paper, we try to answer this question. Can we train classifiers that are robust for all inputs? In other words, we want to achieve global robustness. So here's our contribution, one of our contributions. Our goal is we want to train verifiably robust security classifiers, which provide global robustness guarantee instead of just local robustness guarantee. Now, the first question is, how can we ensure, like before we answer, how can we ensure global robustness? What do we even mean by such robustness? Since we're interested in security applications, so we looked at some threat models of how attackers actually evade those security classifiers. And inspired by the threat models, then we define what we mean by global robustness. So in our running example of detecting fake Twitter accounts, we noticed that in the threat model, the attacker can arbitrarily change the length of profile description feature because the profile description feature is completely within the attacker's control. Or the attacker can spend money to increase the number of followers. So it is actually non-trivial to attract more followers, and attackers purchase and sell these number of followers as services in underground forums, which I'll show more details with our measurement studies later. So what this tells us is attackers tend to do different kinds of large perturbations over different kinds of features. And in addition, these kinds of large perturbations are still constrained in some ways. For example, they're constrained by the cost of perturbing the features. Therefore, we need new notions of robustness that can better capture the threat models of realistic attackers in the world. So in order to train verifiably robust security classifiers, our first contribution is we propose new global robustness properties. We formalize the threat models as properties that eliminate classes of general classes of evasion attacks. And in total, we proposed 6 global robustness properties, and 5 of them are new. Our key idea for formulating the properties is the following. So this is the recipe. We combine security domain knowledge and economic cost measurement study. With the 2 of these things, it can help us summarize general classes of evasion strategies. And then we design properties that can eliminate those classes of evasion strategies. So then we call these global robustness properties. So what we do is these general classes of evasion strategies are focused on capturing low-cost attacks. And in this work, we focus on low-cost attacks that are economically cheap. They cost almost no money for attackers to do. So to analyze those low-cost attacks, we follow 2 steps. The first step is we separate the features into high-cost and low-cost groups. And then the second step is we conduct a measurement study on the economic cost of features. So this is what we do for the Twitter account classifier features. So here I listed all the features used to do the Twitter account classification. And here we separated the features into high cost and low cost groups. A low cost feature is trivial to change. It does not cost attacker non-trivial effort and money to perturb those features. For example, anything related to the profile description, number of tweets, or properties related to the tweets, they are completely within the attacker's control, so they are low-cost features. On the other hand, a feature such as number of followers is really hard to change. Attackers will actually have to purchase and sell these resources in order to change the number of followers feature. So it's high cost. Now, if you notice here, the length of username belong to both categories. Depends on the values for the number of the length of username. It actually depends whether it's high cost or low cost. So we would conduct measurement studies in most of these cases, and then further categorize the high cost and low cost features. So here for the length of username, this is what we did. We crowd over 6,000 for sale posts in an underground forum where attackers are actively buying and selling Twitter accounts to set up their infrastructure in order to spread harmful information on Twitter. So we separated those posts based on the length of username and the account price. So if the length of username is at most 4 characters, the Twitter account price is 3 times of that price compared to, oh, actually it's 5 times of the price compared to if the length of username is longer than 4 characters. This result tells us that if the Twitter account has username length larger than 4, it is low cost feature, and otherwise we consider that range to be high cost feature. Intuitively, it makes sense because there are only so many combinations you can do if you have a very short username length, and it's probably exhausted very early on when any service is established. So these are considered to be more valuable accounts on the market. Now we do several of those economic cost measurement study, and then we can combine the results of the measurement study with domain knowledge to analyze the threat model and define global robustness properties. So here's what we define as monotonicity property for the Twitter account classifier. Using the same set of crowd account price, we measure these account price over the number of followers. Here, each data point is a different fake account. And if it's a larger data point, it means there are more, if it's a larger circle, it means there are more data points concentrated in that area. Overall, from the figure, we can see the trend that as the number of followers increases, the Twitter account price increases as well. So this tells us the threat model attackers operate on in the real world is it's expensive for an attacker to increase the number of followers. However, it's cheap for attackers to decrease the number of followers by blacklisting existing followers. Now we can write a property based on the threat model as the following. So for all inputs, the classifier F is monotonically increasing as the number of followers decreases. What this tells us is the classifier F only makes a more malicious prediction if the attacker makes cheap operation. Here, monotonically increasing output means the classifier F makes a more malicious prediction. And here, if the number of followers decreases, it means the attacker conducts some very cheap, low-cost attack operation. And reversely, this is true, that we allow the classifier to make mistake if the attacker spent money to increase the number of followers. And note that we want the property to hold for all inputs. So this is a global robustness property. So not all features has such continuous cost function. However, given domain knowledge of categories of features, we can still write other properties. Here is an example of the high confidence property. Now the threat model is for the profile description feature, the attacker can arbitrarily change the length of profile description because it's completely within the attacker's control. We can write a property like this. If any data point is classified as malicious with 0.99 confidence, changing the profile description should not make it predicted as benign. We can generalize this to any confidence level. And it doesn't have to be just the profile description feature. It can be any low-cost feature. And the generalized version is our definition of the high confidence property. So what this property means is in the past, we have a confidence score of how much the classifier thinks a data point is malicious. Now we also give the confidence score a meaning of robustness. If the confidence score is higher than a threshold we define, then it also tells us the attacker cannot make trivial operation to evade the classifier and make some malicious data point predicted as benign. So this property also holds for all data points. we can write properties like these as a mathematical formula. And those will be the goals we want to achieve when we train a robust classifier. So here, I just gave you 2 examples of the global robustness properties we defined, and in total we defined 6. Okay, we have a question here from Luca.
Hello, can you hear me?
Yes, I can hear you.
Okay, yeah. So I have a super fast question on the economical part of the attack. So so my question is this? So I understood that this is basically heavily domain dependent, right? Because of course
yes,
the cost changes depending on the domain. So what I'm asking is, might be there some domains where the economical part is not taken into account because there are not many like economical constraints. So I'm thinking about, like, in the case of malware, when you can take a sample, you can perturb it as you wish, depending on the input constraints and the domain constraints, but then you don't pay that much because you have automated tools. So my question is how this can be seen as an economical point of view, or if there is some another meaning of cost in other domains like that, if the question is clear.
Yes, it's clear. Thank you so much. That's a great question. So for malware, it is actually very challenging to incorporate the economic cost angles into that. And what we have done is we focus on the revenue of what a certain type of malware can do.
Okay.
So some malware may just, they probably just steal some information, and it's really hard to characterize revenue, especially if the attack is targeted. But for generic, more generic malware that kind of target the mass population, nowadays the goal is pretty much that they try to monetize the infection. So there will be some angles of revenue. And in our work, what we did is for a cryptojacking malware classifier. So they have features such as the number of web workers, whether it's doing parallel tasks, whether it's using WebAssembly. So all of these are related to the load of web browser. So basically it means if you have a higher load in terms of running more parallel tasks and makes the code run more efficient, like using WebAssembly, then it's the attacker is given the same amount of time, the attacker can make more money. So if the load is lower, then they make less money, and we can design properties as like a monotonically decreasing, that we want them to decrease the load in order to evade. So there are some opportunity to focus on the revenue. In general, however, in general, it is.
No, sorry. I was thinking.
However, in general, it is still very hard. There are some papers that try to argue for functionality of malware to be related to another type of cost. Which is harder to tie to economic costs. You can probably look into how modifying certain feature change the functionality of the malware. Does that sacrifice certain type of operation? And yeah, so there are some opportunity to look into functionality related features as well.
Okay. Thank you.
Thank you. That's a great question. And we're still looking into it. It's really hard to do. Yeah. All right. So I'm going to continue for now. And so now that we know what the properties look like, we want to train a specific type of model that are more suitable to obtain global robustness properties, which we call the logic ensemble model. So the logic ensemble model is a discrete type of model which enables verification of the model for global robustness properties. on a high level, the logic ensemble model is an ensemble of logic rules. The output of the model is the sum of output from all the rules that are true. So here is a toy example of a model with 3 rules regarding username length and number of followers feature for the Twitter account classifier. And I highlighted the trainable parameters in blue. So it's a really simplified example where we can actually add more parameters and extend this if we want to. And in this toy example, if the username length is 1 and number of followers is 50, only the second rule is true. So if we add up all the output from all the rules that are true, we only have 2 as the output. So this is a discrete classifier. Therefore, we can write an integer linear program verifier to verify the properties. The encoding of the classifier is standard. The key thing here is, according to the definition of properties, we can encode violation of the properties as constraints. For example, if we want to check monotonicity, we can encode the violation as the reverse direction of the monotonicity. And then we ask the solver whether there can be any violation of the properties that hold, and also make the constraints of the classifier also hold. If the solver tells us that there is no violation, then the global robustness property holds. So the key thing here is, now that we can verify the properties, we design a new training algorithm to train a classifier that's accurate and also satisfy the properties. So this is our goal. Given a set of global robustness properties, we want to train a classifier with good accuracy that satisfies all the properties we're interested in. Our key idea is we want to use counterexample guided inductive synthesis, or CGS, to achieve the accurate and the robust classifier. CGS is a paradigm initially proposed for program synthesis. I wanted to use this paradigm to synthesize machine learning classifiers. However, the main challenge is there is no generic way to design components of the CGS framework. And it has not been applied for machine learning before. So how can we combine CGS and ML? I'm going to give a high-level overview of what the CGS process looks like before going a bit more into the details. So we have 2 components. One is the verifier, and the other is the trainer. The trainer generates a candidate classifier F for the verifier. And the verifier either produces a counterexample that violates a property for the trainer to fix, or the verifier says there's no more counterexample and the classifier is verified to satisfy the property. So when there's a counterexample, a trainer will take the counterexample and continuously generate a new candidate classifier. This loop will continue until we arrive at a candidate classifier that's our solution, that's both accurate and robust, and has all the properties we want. So the verifier is what I just talked about, the integer linear program verifier. Given a candidate classifier F, if the verifier says there is no counterexample, the classifier is verified to satisfy the property. And by counterexample, we mean an input that violates the property. And the trainer can train classifiers such that this input no longer violates the property. The trainer is the hardest parts in the design, and I'll come back to this in a moment. So this loop continues until it can terminate in 2 conditions. One is if the trainer can no longer generate any more candidate classifier, the process results in a failure. And the other termination condition is the verifier can find a successful classifier F, that F satisfies all the property. And now we have succeeded. This algorithm is guaranteed to terminate. And when the algorithm terminates, if it finds a classifier, the classifier is guaranteed to satisfy the properties, which is the termination condition on the left side. Although we don't guarantee to always find a solution, empirically, we have found accurate classifiers that satisfy all the specified properties. This is true for all the experiments we've run to train hundreds of models over different kinds of data sets. So the main challenge in this whole framework is how to design the training algorithm for the trainer. Our insight here is, since classifier makes similar mistakes, satisfying the property for one input usually applies to multiple inputs too. So I'm first going to describe our intuition to design a trainer, and I'll give a concrete example of how this works in one training loop. So the intuition of the trainer is, we can consider a large ensemble classifier F as all the possible weights that constitute the classifier. Now our goal is we want to find a solution from all the possible weights that give us the properties we want, and also they are accurate. You can think that if you just start from some random weights, it's very likely that the classifier is not accurate, and also it doesn't satisfy any property. So here theta represents all the weights of the classifier. So we have the classifier F of theta, and L is a loss function. So on the left side, in the box, we have the minimization objective that we want to minimize the loss, which gives us accurate classifier. And on the right side, we are subject to some hard constraints. That phi of F theta means the classifier satisfies a series of global robustness properties we're interested in. So how can we do this constraint optimization in training, especially for the right side? So because we're interested in hard constraints, when we want to train certain global robustness properties, we have several templates to write constraints, specifically linear constraints, where each linear constraint will eliminate a set of counterexamples for violating the global robustness properties. So here, A and B, or you can think of these as matrices, and A theta less than or equal to B represent a series of linear constraints, where if the weights satisfy all these linear constraints, then eventually the classifier satisfies the global robustness properties. So we have the part that's optimized for accuracy, that's minimizing the loss, and the other part that optimized for robustness, which at the same time is subject to a lot of linear constraints. So the challenge here is, another challenge here is how can we even optimize a non-differentiable classifier? So what we do is we smooth the logic ensemble classifier such that we have gradients, and using the gradient information, then we can do projected gradient descent to learn what are the optimal weights of the classifier. Now, to be a bit more concrete, I will use this example in our toy example to see how we can generate constraints and train monotonicity property. So we have the same toy example of 3 rules for username length and number of followers feature. And the classifier parameters are highlighted in blue. So each output of the rule is denoted by this R value So we have R0, R1, R2 outputs for the starting classifier F. So the first step is we ask the verifier for the number of followers feature, is it monotonically decreasing? So just to remind the audience here, because it's expensive for attackers to increase the number of followers. If the attacker decreases the number of followers, we want the output to increase, such that the classifier is only going to make a more malicious prediction. Now, the verifier will tell you, no, the number of followers is not monotonically decreasing. And we have found a counterexample. Here, regardless of what the username length feature is, if you increase the number of followers from 50 to 150, originally X activate the second rule, so the output is 2. And now we have X prime that increases the followers to 150. Now f of X prime is 3. So the third rule becomes true instead. So this is actually the reverse. When you increase the number of followers, the output of the classifier increases. So it violates the monotonicity property we want. So how do we fix this? Here's a constraint we can write. We want R1 to be larger than R2 instead. So R1 denote the output of the second rule, and R2 denote the output of the third rule. And this actually already generalizes the counterexample. It generalizes from the concrete counterexample of changing the number of followers from 50 to 150 to a set of counterexamples where you can imagine any number of followers smaller than 100. And then this input increases the number of followers to pass the 100 threshold. So this will be equivalent that the original X will make R1 true and X prime will make R2 true. Now the challenge here is how can we find what are the optimal weights under constraints like this? So the weights are highlighted in blue. So in general, so this is a really simple example. The constraints will be a little more complicated for other properties. But in general, there is no closed form solution to problems like this. For a discrete classifier, we want the optimal accuracy subject to some hard constraints. And also the classifier is non-differentiable. So to solve this problem, we use continuous logic networks, CLN, to smooth the discrete classifier and obtain gradients in order to do gradient guided optimization. So the CLN paper was originally published in iClear 2020. So here's one example operation of what you can do to smooth a discrete classifier. For any inequality, X larger than B, originally it is a step function here, as the blue lines show you. When X is larger than B, you have a jump from 0 to 1. So if you use the sigmoid function to smooth this, now the input of the sigmoid function represents X larger than B. And now you have a more smooth change around when X minus B is around 0. So you can even add temperature to the sigmoid function. For example, you can make the sigmoid function to more closely represent a step function. So it will become a more accurate mimic of the step function. So the details of the smoothing operations can be found in the original paper. So we did a series of those smoothing functions for the classifier. And then this allows us to do gradient guided optimization. In other words, for all the weights, now we have gradients. And since we want to enforce hard constraints, we're able to do projected gradient descent to learn what are the optimal gradients when we optimize the loss function, which improves the accuracy of the classifier. In this toy example, now we have the updated classifier, where R1 and R2 have updated weights. And now we will ask the verify again. Is the number of followers, does it satisfy monotonically decreasing properties now? And the answer is yes. Now just after this one loop, this toy example satisfies the property, and this will stop just for one feature, one property for this one feature. The loop will continue if any of the property is not satisfied for any of the features we're interested in general. So in addition to the high-level training algorithm I just told you about, we also implemented a fixer training framework to further improve the accuracy of the final classifier. So how it works is like the following. Initially, we will boost a classifier F1 and give the sub-classifier F1 to the CGS framework, where we have the verifier and the trainer, verify and the trainer loop to eliminate counterexamples until F1 satisfies the properties we want. And usually after you fix the properties, the accuracy will decrease a little bit from the original subclassifier F1. Now you can boost another subclassifier F2 to increase the accuracy and go through the loop again. So this process can repeat until a number of boosting rounds end, which the user can specify. So after you boost n classifiers, so all of them will become the final classifier that is more accurate than just any single subclassifier. And here we have the booster part and the fixer part. So usually the more boosting rounds you specify, the final classifier will become more accurate. So we have done extensive experiments to evaluate our new training algorithm over 3 public data sets to solve real-world security problems, including detecting cryptojacking, Twitter spam accounts, and Twitter spam URLs. Here are some of our key results for the Twitter spam account classifier. I'm showing you 4 lines for baselines, and the last line, the 5th line, is our results for our larger ensemble model. The first 2 are baselines. That's regular XGBoost training and regular neural network training without incorporating any of the robustness. Next, we have the 3rd and 4th model that are state-of-the-art techniques that try to incorporate some robustness in the training process. Here we have a generalized unconstrained monotonic neural networks model. That's a state-of-the-art technique to include monotonicity property for neural network models and achieve state-of-the-art accuracy. And also we have DL2, which can train neural network models to minimize violation of logical constraints, and also improve accuracy at the same time. So DL2 basically trains local versions of the properties, but does not achieve global properties. So here in the table, we try to show what is the performance of all those 5 models and whether they satisfy the properties we specified for the Twitter spam account classifier. If it's a check mark, it means the property is verified. If it's cross mark, we have found violations of the property. If it's a question mark, we cannot verify the model yet for that property, but we also haven't found counterexamples so far. However, since what we do for DL2 models is gradient guided attack, so usually you can try harder and find out stronger gradient guided attacks to find violations of the properties. So our first observation is none of the state-of-the-art methods can achieve all 5 properties at the same time. Basically, the best is the generalized UMN model, which can achieve the monotonicity property, but cannot achieve any other properties. And in comparison, we are the first to train a verifiably robust classifier with all 5 properties. If we compare the performance to previous robust methods, if we look at F1 score of our large ensemble model versus generalized UMN and DL2 models, we have comparable performance to previous methods that cannot achieve the properties. So what this means is previously, a lot of related work focused on training local robustness properties. And we don't have to pay like noticeable performance drop in order to achieve global versions of the properties instead. So to conclude the talk, we argue that security classifiers need new notions of global robustness properties. We have designed a new training algorithm to achieve these properties. And lastly, our key result is we're the first to train classifiers that satisfy 5 new properties for real-world security applications at the same time. And we have open source the code on GitHub. Now I'm happy to take questions. And this concludes the presentation. And Luca has some question.
So first of all, thank you for the talk. It was very, very interesting. And it inspired me another question. Sorry, it's gonna be like this for all the talk. So there is like hearing all the rules. I was thinking about I don't know if you're familiar with like automata learning, like when you're trying basically to understand. I mean, maybe it's like more like of a visionary question rather than like a question on the work itself, because I see like something similar. Like in automata learning, you're trying to learn a finite state automatum. Sorry, my Latin is bad. That is basically encoding transition from one state to the other to determine a certain property. And here I see that you're basically encoding logical expression, and then you basically and you do the training that you mentioned. So my question is, are these 2 approaches? I mean, how these 2 approaches might be related, if there is some relation? Because like the question might be ill posed, just like a curiosity that I had like while listening to the talk. If it's the case, otherwise just say no and I'm fine.
Well, thank you for a very interesting question. I am not an expert on automata learning. I wonder, so this is just my guess. I wonder whether you will start from some basic structure of automatas and then iteratively try to improve that based on some procedure.
Mm-hmm. Because basically, I mean, you have a matrix and then you feel basically the transition from a state to the other, but maybe maybe it's like not so related. Like maybe, I mean, intuitively they might be, but I understand now that maybe they are too far away for construction, because there are rules there that you want to enforce. That's why I was like thinking about that.
Okay, so in terms of the space, so I don't know how large your matrix can be in terms of the space you start with. I imagine that will be like exponential to the things you care about. You would have a combinatorial.
Okay, yeah, you're
like,
right.
Connections. So when we train models, so the space, maybe the space is going to be even larger, because so here is the learning parts. If you have a large data set with say hundreds of thousands of training data, then you can decide whether, so here I think, yeah, let's consider the binary classification case.
Mhm.
If it's binary classification case, you consider whether any training data point is malicious or benign. So it's like 2 to the number of training data points, possible classifiers. So here, maybe this, I'm just guessing, maybe the space is relatively larger. And there is some machine learning angle where it can help you more effectively reduce to what is the initial accurate classifier, and also how, when we improve it, how can we also guide the classifier to be a more accurate one. So we are not, well, it's not possible to enumerate such a large space of all the possible classifiers. So the learning here comes in, and also I don't know whether in automata learning, whether you will rely on some type of heuristics or rules to update this whole thing. Maybe, so I'm just talking about this totally based on an amateur who doesn't know anything about this. Maybe when your space gets large enough, I don't know if machine learning can come into play as well. Yeah. Okay, no, sorry, that was like a very, very super, because I'm not like, I mean, I only know a few things about automata learning, but then I got curious, but I think I got your point. Thank you for the answer. Sorry for this strange question. Like, thank you. Oh, no problem. It's always interesting trying to connect different things together.
Let's see if we have other questions from the audience. There is a question.
Do you hear me?
Yes, we can.
Thank you for your presentation, and I have two questions about slide number 12 and 13. You determined the threshold for username length equal to 4. I want to know how did you determine the number 4 for the this threshold? Because I see the high difference between the account price equal for a username with length of 4 and 5. How do you find and define this threshold? And if you answer this, I will ask my next question. Thank you.
Oh, thank you for the great question. So, so we actually have another detail of how we determined the username length for. That's so in the underground forum, they have a tag. Oh, okay. So, so the sellers would typically mention whether the length of character is under a certain username. Like they would make a tag like 3 to 4 characters or under 4 characters. So from the seller's perspective, they naturally consider this to be a short enough length of username. So that's one aspect. They consider this to be a different category than longer than 4 characters. And in addition, we also try to separate this average account price by different characters. So we tried 3, we tried 5 and 6. And difference in the average account price is not as large as this one. So here I'm showing that if the username length is at most 4 characters, you have 5 times the price of the other accounts with longer username length. So based on the combination of these observations, in our property specifications, we use 4 characters. But in general, our technique can generalize to different specifications. So here is more of what we consider to be the domain knowledge in this case.
Thank you so much. And in the next slide, we have we have some accounts with 100K followers with lower price of 50K followers. What's the attribute and what's the properties of these accounts that has they have a lower price with higher followers. Is there noise or not?
This is a great point. Thank you. So in the whole, when we model the trend, we consider that to be the outliers. So are you talking about like the data points near 100K number of followers where they're low price? So Irish is muted?
Yeah, yes.
Okay.
We have three circle in bottom of 100.
Yes. Also, there are some other data points like under around 50,000.
They are outliers, yes?
Yes, we consider them to be outliers because so it's more of a supply and demand thing. There may be occasionally some supplier who have maintained those Twitter accounts with a lot of followers and they will sell them at a relatively low price. But if for anybody who wants to buy new accounts, there aren't that many available like this. The majority available will still be a more expensive account. And in addition, we actually also discover there's another like accounts follower increasing service. So they would, some attackers will explicitly sell 20,000 followers for a flat price. So if they want to increase 50,000 followers, that's another price. So the overall market is still, if attackers want to buy more followers, either they can buy a new account with more followers or they just purchase this follower increasing service. That's going to be expensive. What you mentioned is outlier because these are very occasional corner cases where a certain account is available, but not generally the case.
Thank you so much. I appreciate it.
Thank you. Thank you.
We have time for a last question. Let's see if there are other questions from the audience. It seems no on Zoom. Let me check.
Stefan?
Hi, how expensive is the training versus XGBoost? Does it take twice as long or 10 times as long to train a model the same amount of compute?
Regular. For a large data.
Sorry to interrupt, but we couldn't hear you. Like the answer you gave, we couldn't hear you, so I don't know what happened.
Oh, can you hear me now?
Yeah.
Yes.
Sorry.
Okay, sorry. All right, let me start again. So, so in terms of training down, it depends on the data set. So XGBoost.
Now we can again hear you, just not continuously, basically.
Can you hear me now?
Yes, now yes.
All right, let me try. Oh.
The microphone is moving.
Okay, let me try not to move. Okay. All right. So if I remember correctly, to train cryptojacking data sets for our specified robustness properties in 5 properties in total is about 30 minutes. And the median time to train robust Twitter spam accounts depends on different kinds of property configuration, it will be like 3 hours, and the median time for the largest data set to spam URLs will be median time is 3 days. So these are our robust training time. And the size of data set is the cryptojacking is thousands of training data points. Twitter spam is tens of thousands. And the largest Twitter spam URLs, not the accounts, the URLs, we have 400,000 in total. And the training data is like 280,000 training points. In comparison, regular training may just be, depends on data set, maybe from a few minutes to like 15 minutes. So the slowdown is that like 100? I don't know if that characterized as 100 times slowdown. So the slowdown is significant, but it's kind of it's widely accepted as in the robust training research literature, that usually it is worthwhile to pay for this time cost because it's a one-time cost. And then you can obtain a robust model, and at test time, you don't pay the top cost anymore. You just deploy the model. So I hope, can you hear?
Yes, I can still hear you.
Okay, okay. I don't know whether the mic stopped working.
No, I was 100 times is significant. A industrial malware model takes about maybe a day or two to train. So 100 times increase in cost would be prohibitive for a malware model company. So maybe with some optimizations, because your code is probably not as optimized as XGBoost.
Yes.
You can get some major speedups, but yeah. Well, thank you very much.
Yeah, this is a great point. Thank you. So we're also looking into how can we scale this, because this is the first paper we did. So we focus on only using this discrete type of model. But there are ways where you can speed this up. For example, if you just have a part of model to be this discrete model where you have properties, and the other model to be actually boost. When you combine these, can you still maintain some of the properties? Or if you just combine this with a neural network model, which is fast to train, also more accurate overall. We're studying whether by combination, you can also keep some properties you're interested in. So scaling up is definitely a challenge and also a direction we're looking into.
That's a really cool idea. Well, thank you very much. It was a great talk.
Thank you. Thank you for the great question.
Thank you again, Yizheng, for the great presentation. A little announce for all the audience. The 24th of June, there is the deadline of the Artificial Intelligence and Security Workshop co-located with CCS that me, Yizheng, and Florian Tremer are organizing. And so we are looking forward to receive your paper. That will be held in a mixed format, so you can participate both in person or online as you wish. This is everything from my side. So I leave the stage to Maura for concluding.
Yes, thank you a lot, Yizheng, for your talk, and congratulations on the paper, because it's amazing. I read it the other day, and it was really intriguing. So thank you a lot for joining today.
And thank you for inviting me, and thank you for listening to the talk. Thank you so much.
Thank you for accepting.
And of course, thank you all people who joined the seminar today, and I'll see you next time.